had lab today, and then I got up this morning and looked at our schedule and we have lab this week. We'll do lab next week. So I'm going to review the integrated rate law stuff. That's why I gave you that sheet. I will give you this on the test, so you don't have to memorize these or learn how to derive them. But we'll just apply them or practice a little bit. And then we'll see how time goes. I might try to do collision theory stuff, but I think I would rather review this first. Let me start with a rate law stuff. Okay, this is a review. So, and I'm going back to rate law for just a second. This is an integrated rate law. But if you have this reaction, so that double the concentration of A and the rate quadrupled, what is the order? For rate law, its rate equals the constant, and it's this we're asking for. But if I did this, parentheses. Let me put A in the box just to get it out of the way. All right. If you double, put a 2 here, I'll just say X there, and this ends up being 4X, what is this? It's not 1 because that would be, if you doubled that, then it would be this. If you had this squared, then it's 2 times 2 is 4. And if we're not going as far as 3, but if you had 3, the rate would change by 8. Do you follow that? So what's the answer to this one? And this is the order, of course. So if you multiply that by 2, which forces this to be quadrupled, what goes here? Does that make sense? That's easy, right? Do you know what you would put for that? What is the rate law? Starts like that, right? You could do this, right? concentration C6, H5 into Cl. What goes here? What would you put here? And what would you put here? 0. And ultimately, the way this is generally written, you drop that off. And again, you don't have to write the 1. So usually you just see it like that. Oh, I left off the K. My bad. There is a K there. The way it comes. So if you wrote this is actually all there is to the rate law. Of course, I'm going to mark it full time. It's dying. This one will go. If I triple this, what does that do to the rate? Triple the concentration of A, meaning I stick a 3 in there.
6 times?
What? Yes. It's 3 times 3, so that makes 9. It's 9. All right. Reduced to 1/3, meaning it's times 1. What does that equal? 1/9 the rate. All right, maybe I'll just go on with the integrated rate law stuff. So what I just gave you, somebody put their samples right here. That's not a sensible place to put their samples. Go on to, so that sheet I just gave you, like I said, I'll give you those for the test. Or a not. put the little 0 here, that means initial, so I'm just going to erase that. Okay, and P is initial rate. So you have on your sheet there equation for first order, equation for second order of this form, and equation for 0 order. The first thing we need to do is figure out the order. So this is kind of like just talking about rate law, meaning we have to find out so you remember how to do this? If you want to do it by equation, rather than just looking at the data, you go, first you need to pick one that has 2 the same, like this. So initial concentration of A is the same for this trial as this trial. But here, initial concentration is different. So let's go with that first. So it's 1 and 2. So we're just going to go rate 1, rate 2, K, concentration, A, for 1, and we plug in the values. Initial rate for 1 is 0.470. Initial rate for 2 is 1.880. Okay, initial concentration for A for 1 is 0.70. 720. It's the same down here. Really, the brackets mean concentration, so I could start doing this now. D, K doesn't need to be there. That's right. So you only need the K at the front. And 1 for B is 0.180. And 0.720. So these two are obviously identical. K times this, we can take away. 470. Actually, we're going to do that. .470 divided by 1.880. We get 0.25. So this part is 0.25. If I wanted to write that as a fraction, though, what would I put? You can go 1 over 4 or 0.25. We'll see which one's more convenient. 180 divided by 720 equals, we'll without going any further, it's obvious what n is, right? N doesn't change the value, so what is n? 1. So what we did is just found it for b. N is 1. Now we need one where b stays constant and a changes. They're not always consecutive, but notice 0.180, 0.180. So we'll do 1 and 3 this time. And that's going to make b drop out. The rate for 1 is this, the rate for 2 is 0.117. For A, so I'll write it out even though I know it's going away. 70. A was 17. This one is. Rate for 3 is 117. A is 60. That goes away. I'm going to go ahead and calculate that. 0.470 divided by 0.117. It's about 4, which I think is what we're going to want. This is the same as 0.720 divided by 0.360. 2 m equals 4, 0, and some change. So what is m? 2. These don't come out exact because there's always a little bit of experimental error. So the first question is, and for A, it was 2. For B, it was 1. What's the overall? It's 3. And the last question is, so you can find the order for each one that easily gives you the overall order. And then the last question is, what is the value of k? So, I erased everything, but you just pick one of them. I'll just use trial 1. Trial 1. Concentration B for trial 1 is 0.180. And the rate. So I'm going to use those values to plug into A is 2, B is 1, I could just leave the 1 off. And we just plug it in and we find K. So we're really looking for rate divided by times B. That equals K. Divide both sides by this. So A is 0.1 .720 squared, B is 0.180. 0.720 times 0.720 times 0.180. So I got 0.740. Pretty significant figures. 0.740 divided by 0.0933. The units, I should have given you that formula for units. Overall order is 3. So it's 3 minus 1 is 2. 1 minus 3 is minus 2. Those are the units for K. That's how those types of problems work.
The overall order is 3. How did we get 2 for the equation for A? Is that just how it is?
Rate equals K. If B was 1, the overall order, you add these two together.
Okay.
That's where you get overall.
That's the end of the end.
Huh?
That's the end of the end.
Yeah, n plus n, if you want to think of it that way. This. This, B goes from 1 to 3. That's essentially like saying times 3, right? So what is the rate changed by? It's kind of same as the previous question. If it increases from 0.1 to 0.3, that's the same thing as saying 3 times B. If this is squared, what does it do to the rate?
9.
Yep, it's 3 times 3, so the rate would go by 9. Going back to rates. Maybe we're good on this stuff. You guys still okay with this stuff? You do? felt like I was losing you. So maybe I can go on to collision theory. I didn't make a PowerPoint.
No, it's not. There's no only thing we're doing is anything else just kind of seems easy, but mixing up the code order,
So this is collision theory. One generality that goes along with collision theory is these three facts. The reaction is proportional to the rate at which collisions happen. So if reactant A and reactant B are going to react, they have to come into contact. So we just call that a collision. So at a certain temperature, let's say you've got liquids, doesn't matter if it's a liquid or a gas, everything's moving out around at a certain speed. And there is an average rate of collision of the two reactants, reactant 1 and reactant B, or I could say A and B, reactant A and B. So they bump into each other, and it's collisions per time. So the more collisions per time, the faster the rate will go. That makes intuitive sense, right? Two other important facts, though. The energy at which they hit each other matters, so they might bump into each other without enough energy to make the reaction go. Or they might hit each other with enough energy, it just depends on how fast they go. So I'll remind you of this. Let's call that. If you go at a higher temperature, you get a lower peak, but you get a longer tail. This is so there's a certain number of molecules like here. Some number of molecules here has this amount of energy, and then you have a peak number of molecules that is the average, but you have more molecules down here if T is high. So if, the point is, if you increase the temperature, you have more molecules. Like if I just chose this as a cutoff energy, I have this many molecules up at this higher temperature. Whereas the blue one at the lower temperature only had some portion of that. This goes out asymptotically. So this is like the distribution of energy. At higher temperature, at lower temperature, you have this higher peak. The temperature you would measure, if you were measuring this at a lower temperature, and then the same system at a higher temperature, you would find, now I have to put temperature here. All right, so anyway, what I'm trying to say is the higher temperature, more of the molecules have higher energy. So if you have higher temperature, the molecules banging into each other have a better odds of reacting because some of them have a low temperature. Let's say you need this amount of energy to make the reaction go. At a lower temperature, you have more of them below that. At a higher temperature, you have, I should say it up here. At a lower temperature, you have less of them that have that energy. At a higher temperature, you have more of them that have that energy. So if you think about temperature in number 2 here, the energy they need to impact, more of the impact will have the right amount of energy for the reaction. So that'll increase the temperature, the reaction rate for that reason. No, that was number 3, the energy. Orientation matters too. I stuck this down here at the bottom. But this is CO banging into O2, trying to become CO2. And this is just saying if they bang into each other like this at the top, you won't get the reaction. And if they bang into each other at this orientation, you will get the reaction. So 3 things that matter. What I really want you to take away here, though, is increasing the temperature will increase the rate. It actually changes K due to temperature. I should say everything we've done up to now, I do that set of data, it's all done at one temperature. And that's why the K for all the trial 1, trial 2, trial 3 will all be the same. So you're comparing apples to apples. If you change the temperature, you change K and you increase the rate. I did this last semester. Did you guys do energy diagrams last semester in other 12, 11 classes? This came up when you talked about delta H. The energy diagram. You can think of this as time. It's frequently called the reaction coordinate. Or you can think of it as the reaction, the progression of the reaction, but if you think of it as time, it works intuitively. But time-wise, you put 2 things into a vessel and you want them to react. Right there at the beginning, early in time, let me do this. Early in time, you got nothing but reactants. And then something happens, and then later you have products. Energy going in to get you from this is energy. Energy going in is breaking bonds, and then energy comes out when bonds form. And the difference between the strength of the bonds you're breaking and the strength of the bonds you're forming is this, and that's delta H. So from last semester, it probably came, if this came up, it was when you talked about delta H. Is this one endothermic or exothermic? Do you remember this? If you start at this amount of energy and you end at this amount of energy, that's exothermic. That means some energy came out. I could have drawn this and had the reactants come out here, and then you'd have a delta H here. So here the delta H is negative. You go from up here to down here. If the products came out there, then energy goes up, and that would be endothermic. But I've got exothermic here just for an example. And this distance from where the reactants are up to here, EA is always used as a symbol. EA equals activation energy. A is activation, E is energy. So that's one thing chemists will do experiments to find out what is the reaction energy. the actual physical system. So when things bang into each other at the right orientation, things shift a little bit weird way right there at that instant. That thing where it looks kind of weird before it comes apart into two new pieces, that's called the activated complex. That exists right here too. Right here is so if you're running this reaction and you can freeze it right here, let's say for just two molecules who have banged into each other with enough energy in the right orientation, everything shifts just a little bit just before everything comes apart into the new things. That thing that sits like that is called the activated complex. Just a vocabulary word. But having written that, having drawn that, there's this. And again, this is like I've been telling you for 2 weeks. This equation is not something I can give you intuitive understanding as to why it's this way. I didn't print this out. I forgot to print something. I had to scramble when I realized we weren't having print these out so I can leave the video. This is called the Arrhenius equation. And it's related to collision theory. It's probably worth mentioning. Rate laws are concentration and I'll say concentration versus rate. When we're dealing with rate laws, we're going rate equals K, concentration A, concentration B, and then we're relating these concentrations to the rate. Integrated rate laws are concentration versus time. When I was talking all this time, who was talking about rate law? I didn't go over integrated rate law. I'll do that after I do our rankings. I wanted to review integrated rate law, but what I did is review rate law. Okay, I'll review integrated rate law in a little bit. But earlier I was doing nothing but rate law. So we didn't do any of this yet today. We did all of this dealing with this equation. And the integrated rate law is see the sheet I gave you. So that has things like, for the first order you see, I'll just pick one of these because there's several of them. At time t equals natural log of A. In these, we're relating temperature and concentration. So that's why I put this here. Not temperature, time. T is time. So time, and then Arrhenius, the one I'm about to show you is, this is, write down Arrhenius. I should have printed that out. Arrhenius equation is K equals negative EA over RT. So here we're actually relating temperature to K. So So like I said, in Arrhenius, we're showing how K changes the temperature. I've moved on to this now. So just as a way to help you keep track of all these formulas and graphs, let me get this out of the way. So this is the Arrhenius equation. Again, I'll give you any of these on the test. But the whole point is Arrhenius is and based on those first three things I showed you, as temperature increases, the rate increases. So you expect K to increase. Okay. There's a couple more equations. I wish I had printed this one out for you, but just like these, there's several of them. This, it doesn't matter what order, but you can derive from here, you can get to negative E R 1 over T natural log A copy that out of the book. They didn't put the brackets around it. They should have. So, and it's Y equals. So here X relates to K versus temperature. How K relates to temperature. So K is over here, and we got the natural log out. Temperature is here. This is a constant for a reaction, and this is initial, whatever the initial is. So what would I do with this equation? Remove this. So I'm going to go through this example. This is running out of good markers. That you're given. So generally, if someone does a reaction, they'll go, I'm going to do this reaction at this temperature. Oh, temperature has B and K. I didn't mention that. Here's all the trials. So they literally did this experiment this many times, 5 times. And they also measured K for each one of these. And for these, this is what we got, 3.52, 7. That's the data they got. But really what we want to graph, we've got to do anything. R is that constant. It's a joules per mole K. So we can find the energy of activation from data like this. But what we really need is 1 over t, and we need the natural log of this. So you would take your data, and the first thing you would do is do 1 over t. This is 1.80. It's 10 to the negative 3. So that's what you get if you do 1 divided by this, you get that. 1 divided by this, you get that. And then you need natural log of k. So there's your new data. And then if you graph this, you will see a linear trend. So your y value is, your x value is 1 over t, and you will see something like that. If you graph it, 1, 2, 3, 4, 5, wherever the data points are, you should get a straight line. If this is experimental data, the data points will be generally straight. You would have to do a line of best fit, and you would use that line of best fit to find the slope, and then you can find the energy of activation that way. You can, there's a couple more equations here. Again, I'll give you these on the test. But you can go from here to this. 1 over k2. And the more useful one is solve for energy of activation. Negative r. I'm really writing these, so I'll have them on the board. So there's this equation and this equation. Once I upload this, I have all that here. So here's the Arrhenius equation. You can use algebra to get here. Actually, you use calculus to get here. And then you can use rules of algebra to get to this one in the bottom left, and then you solve for energy of activation on the right. So I needed to have those up. Okay, so this question, what is the activation energy for this reaction? That's what I'm looking for. I'm trying to find EA based on all this data. Experimental data, like I said, those might not line up in a perfect line. So then the best thing to do is to use this equation and find the slope, and then use this constant value to help you find energy of activation. I think that's all I need going forward. So I can erase this. So if I wanted to know the slope, we still do rise over run. So this, and you want to use the full range of this if you're doing the slope. So across here is, down here is this, and up here is this one. So I'm going to use those two data points. And then here, 1 over t. Well, so I'm going to use 1.28 times 10. 10 -3. That looks backwards. I want to use the one that goes with 14, so this was 1.08. 1.80 times 10 to the -3. And this one that goes with this is 1.28. Oh no, that's what I'm going to do down here. Up here, so if we found the slope, what am I doing? Rise is so that's this. That over rate. Minus I did this in a spreadsheet before. I'm running out of room on the board. Initial, final minus initial. Well, let me just write it down without going through it. Either way, you get, so if you solve that, you get, solve all that tedious math, you get and then that means that slope, this is the slope. The slope has to be equal to this. So negative EA. This is negative. So this equals this. And then we want to solve for EA. Solve that tedious math and you get negative 2.2, and then you've got R equals 8.314. So multiply both sides by that. .2 times 8.314. times 8.4. Yeah, 18.3. This is negative. Ultimately, you get the energy of activation. I feel like I've messed up the math already. This is what I'm trying to do. .2 times 10 to the 4, it is negative. 1.8, is that what I got? So they put it in scientific notation. Since I gave you A, B, C, D, and E on a test, it should be there in some form. And that's 1, 8, 1, 2, 3, 4, 5. And this comes out in kilojoules per mole, joules per mole. So if you use this formula, the energy of activation comes out to joules per mole, or you could say kilojoules per mole. So I like to go through all the math. I know I skipped a bit there, just so you see it, but this is the way you solve these problems, so it's kind of inevitable, all this algebra. The second half of this is you could solve this using this. You could just solve for energy of activation and do it like this. But the reason we use the slope, we use this form. We use this form and we find the slope and then set it equal to this is because of experimental error. So that line of best fit is what defines the slope, but the line of best fit isn't necessarily going through every data point. It's just the best representation of the data given experimental error. The other way you could do it, though, is you could use this equation and kind of go more directly towards the answer. And that would give you the same energy of activation. And so, for instance, if I gave you some data in a question that said, what is the energy of activation? And I give you some temperatures, and I give you some Ks, and I would give you, here's a graph, natural log of K and 1 over T, and it looked like this, and it had a line there, and just the way you would see in Excel, you would have for that. Then you would use this slope, set it equal to this, and then solve for energy of activation that way. If you saw data that looked like that, then you could use that to solve it. If the data points lined up nice and neat along a straight line, then you can use this formula. But if it's messy experimental data, you have to use y equals mx plus b, find the slope. Truthfully, the way this example goes, it uses the first data point and the last data point to find the slope. But you would only do that if you had a nice, neat, straight line. If you had messy data that looked more like that, this line that I'm drawing is something that, well, I usually do it in Excel. So Excel would give me this line and the equation of the line, and I could get slope directly and then make that equal to this and then solve for heating. See what I'm saying? So here's me going through it a second time using that other formula. If you were given a question like this one, let me rewrite it. This one doesn't give you data. Sorry, I didn't upload that before class. This is, what's it called? Check your learning. Well, not 13. This one gives us mole. They're giving us this. Let me write it like this. Temperature at 650 is 1.66, and then at 700. Instance 1, instance 2, we could call them trials. This is essentially what it's giving us, without me writing a question. If that's all you have, it kind of doesn't matter whether you graph it and find the slope or not. You've only got 2 data points, but those 2 data points is enough to use this equation. So the second question just gives you 2 data points. You might as well just do it this way. You see what I'm saying? If you find a line of best fit between two points, you're going to get a straight line between those 2 points. And the slope of that line is going to be exactly the same as the rise over run method. See what I'm saying? So this time, I'm going to use this equation. So energy activation equals negative 8.314. I'm going to leave the units out because I know that this comes out to joules per mole. Joules per mole Kelvin would be this. And then K2. So I'm solving like this. Natural log of 1.66. Calculator, scientific. 1.66. Natural log equals. I'm going to keep some extra digits just because we're using logs. Minus. I just did K1. Just so I don't get messed up. So I just did this one. And since I've got labeled as 1 here, I'm going to keep it like that. 739. I'll just keep a bunch of digits because I use log. 1 over T, 2, 700, 1 divided by 700. These should really be this. 650, 1 divided by 650. 32.0001277 minus 0.506817. All of that equals I could go to 3 significant figures at this point. There was a 0 there. I'll stop at that. And this came out negative because of that negative. I get about 113. Well, I get 1130704. If I kept 3 significant figures, it's 113000. That's 113. Yeah, they rounded it down to 2 digits. I don't know why they did. We need to review some of this, but I think we should just go back and review it. So we reviewed rate law. Let's review integrated rate law. And then we'll do more with Arrhenius next time. I'm sure I'll finish this chapter this week. Connection mechanisms. Analysis is kind of obvious. And I'll probably start just a little bit of chemical equilibrium before test 1. But let's try to get kinetics kind of under both. Okay, now integrated rate law for real. So now you can use that page I gave you. So they give us data. SO2Cl2. This is the reaction. A lot of these problems, they do decomposition. The particular type of reaction is decomposition. That means you have one thing and it splits into more stuff. If it's decomposition, it's necessarily going to have a rate law that only has one concentration, meaning it's going to be A, concentration of A, whatever N happens to be, there's never going to be a B here. So we're always going to be locked into this without a B to an N if it's decomposition. To give us this data, data's a little hard to read the way they put it in. There's their data. Okay. It says to do this graphically. On a test, I would graph this for you. You guys graphed with Excel last semester? I probably need to make a graph for you for these, but I do need to put this on D2L. So you can do it yourself. When I put these on D2L, I'll include the graph. But not as prepared today as I could be, so I'll go through at least a couple of these, but I'm going to have to graph them. So this is what they're asking you to do, but like I said, I will graph it for you. First thing we need to do is figure out whether this is first order, second order, or third order. So here's what I'm going to do. I'm going to take the concentration. That has the concentration. The one that has just concentration is 0. Has natural log. This equals 1 divided by this. So far, this has nothing to do what I had to do. Okay, here's what I'm going to do. I'm going to go time this. So you might have a lab that has you do this, but I'm not going to have you do this on the test, so I wouldn't say practice this. I'm going to do time. I'm going to do time. That's right. Let's see. See if I can get all these on the same screen. If you look at this, the graph I just made 1 over A on the y-axis. Looking at that graph, what does it tell you? Say again? What I would say is, since it's not linear in the 1 over A, what I would say is it's not second order. Looking at this, did I put the data in right? Because both of these look linear to me. I would give you data that's clearly linear or not. So I think that's unclear. Let's do this. supposedly do half-lives, because those are just calculations. But I'm so not prepared to review integrated rate law. Maybe we'll just eat the last 15 minutes and screw it. We'll review this on Friday, and I'll have these graphs so you can see the graphs. Let me check something with you before you leave. Let me check something here. Look at this before you start leaving. Okay, I found this website. I'll upload this. I just call this practice stuff. So this is practice rate law stuff. I've been using this today. This that says practice integrated rate law stuff. You can find this at the University of Calgary. It does this. What I would tell you to do is just look at the solution. So they've got one that's got data like I wrote on the board. But if you click on it and you look at this, look at the left axis. This is just concentration. This is natural log of concentration. This is 1 over natural log of concentration. So what you would tell from this is, what can you tell from looking at those three graphs? That it's first order because it's linear. That's what I was trying to do in real time. I was just wasting your time, so but use that. Look at this. I think this will be clear. Just look at that website. Me stumbling around trying to grasp things, it's just eating up your brain.